we're going to look at creating a practical TrustZone program today. So after the last couple of days, we've seen that security partitioning is crucial to defending against a software attack on our IoT device. So what we're going to do is have a look at some of the crucial things that we need to do to create a program that allows us to use TrustZone to create a secure application. There is a nice example that's available in the pack installer. So if we go into the pack installer, there's the devices tab and then the ARM section. And then over in the examples tab at the bottom, there are a set of TrustZone examples that demonstrate how to create a suitable program both with and without the real-time operating system. So we'll be talking about this today, but after the presentation, if you want to go through and have a look at this example, you should be able to build it, and it will also run in simulation as well, so you can step through without the need for any real hardware. So first of all, we need to make sure that our tool chain is capable of building code to work with the security extensions within Cortex-M 33. So there are a number of commonly used compilers, the GCC compiler, IAR, and today we'll predominantly be using the Kyle MDK ARM. So inside here is the ARM compiler, and the current version of the MDK actually has two versions of the compiler, in version 5 and version 6. So version 6 is the one that you need to use. That is able to generate the additional secure gateway instructions. So before we go anywhere, we need to make sure that we have a suitable compiler. And if you are using the Kyle tools, then the version 6 is included in each of the different versions, but it's only the Plus and Pro that it's enabled to create secure applications. Now, when we're designing a program, we have our two partitions. So we have the secure world, and then we have the non-secure world. When the processor starts execution, it will start in the secure state. So we'll boot into the secure state. There, we need to run all of our startup code that will configure the security attribution unit, set up any peripherals that we want, and then we will jump over into the non-secure code. So in the non-secure area, this is where the bulk of our project is executing. So this can be developed kind of as normal. And then when we need to access secure functions and data, we can make calls to functions that are in the secure world. These will execute and then return back to the non-secure code. So essentially, we have a small bit of startup code in here, and then we pass over, and our main execution is now within the non-secure area. And we want to try really to keep the amount of code in the secure world as small as possible. Okay, so we can easily monitor it, and it just provides the security functionality. So to construct that type of project, essentially, the best way to create these partitions is to have two separate projects. So we create one for the secure world and we create one for the non-secure world. So if we think back to the very first week, we discussed creating a bootloader and main application code, and this really follows exactly those principles. So the secure code will be linked down to the start of the flash memory. So when the chip starts, we'll start executing the secure project. We'll do the necessary code, which we'll cover in a little bit, to set up the environment, and then we'll jump to the non-secure code. So this is linked to a higher address. So our initial reset is sitting in a higher start of a higher flash sector, and here we can move the non-secure vector table and relocate that to the start of our non-secure code. We also have our veneer table here. So this is effectively a jump table, so that when we're running the secure code, the non-secure code, we can make a call to a secure function. So here we will jump to the veneer table, which has the secure gateway instruction, and then we will branch to the function that's in the main area of the secure code. So we have to lay out our two applications so that they're allocated secure resources, and then the rest of the code is sitting in the non-secure area. Now, within the Kyle tools, when we're defining our secure project, we can select the software model. So here we can say that we're building for the secure world. We also have a choice of the compiler library that we're going to use, so microlib or the default ARM compiler libraries. And then normally in here, we can define the memory layout for the target by defining execution and data regions. Now, this we can sort of create as a dialog, and underneath the tool then creates the linker scatter file, which is the linker input file. Now, ultimately, we're going to create the scatter file with a separate tool that we'll look at later. So for these projects, these menu options are disabled, and we'll see how that's done in a little bit. Okay, it's not absolutely necessary, but if we create the scatter file with an external tool, every time we recompile, if this is enabled, it will overwrite the existing scatter file. So we need to switch it off. Now, when we create our program, we can set it up exactly the same way as we discussed in week one. So in the runtime environment, we enable the device startup and the CMSIS support, and this will create us a minimal program that will get us up to main. So in our secure world, we can do exactly the same thing. So now we have the startup code, which is the interrupt vector. We have the system code, so this runs before we reach main, and it will configure all of the main system peripherals. And with the secure code, we now have an additional header file, which is this partition file. So this now carries all of the definitions for the security attribution unit. So now when the device starts up, it will boot into the system code. It will configure the TrustZone security attribution unit. So by the time we reach main, the chip is now partitioned between secure and non-secure regions. We can then run any additional code that we want in main before we then jump to the non-secure code. So we've got one additional file here that again is templated code that we can configure. So here in our project, again, exactly the same layout as we started with a couple of weeks ago. So we have our CMSIS, and then we have our device files, and then we have our startup code, again with this one additional partition file. And in here for reference is also the linker scatter file as well. So when we build, we can define all of our regions within the scatter file. Now the partition file is again one of these templated files. So underneath this template is a set of hash defines. So here we can go through and we can configure each of the the security attribution unit regions, a start address, end address, and the type of region that we want it to be, secure or non-secure callable. Then we can enable it so that as soon as configuration is finished, we have a partition chip. Underneath here, we have other options which we'll come to for controlling the global features of TrustZone and also routing interrupts as well. So this is all gathered into one easy, convenient place. So now in the linker, project options, we've disabled the target memory layout. So here we've disabled those options. So now we will use this default scatter file, and this is just a text file. And inside here, again, in this particular version, we have a templated version, and we can configure the flash region and the RAM regions that the secure project is going to use. And these, of course, need to match up to the secure regions that we've defined in the partition file. In addition, here we can then set up the stack and heap size as well. So now when we build, we'll match the layout that we've defined for the partitions on our chip. And there's another important command down the bottom here for the linker, in that it will generate this veneer table. So this little library file is our jump table, which we'll need to locate into the non-secure callable region. Okay, so this provides the entry points for the non-secure code. Okay. Now, depending on your tool or version of card, this may be an additional linker file. If you're using another tool, this may also just be a C file that provides those symbols. So now once we've created the default of the program, we can add main. So here we have a code template. So this will add the initial main code for our secure project. And in here, this is very similar to the code that we looked at the very beginning for our bootloader. So what we need to do, we start into our secure region, we start to execute the secure main. So once we've done all the configuration necessary, we need to perform a sort of software reset to jump us into the non-secure code. Now, normally at reset, we have the first 4 bytes of memory as our main stack pointer. So that value is loaded by the hardware into R13, the main stack pointer. And then the value that's held in the next 4 bytes is the address of the reset handler. So that value is loaded into the program counter. But now this is not sitting on the hardware reset vector. So we have to provide software in here that will do that for us. So in our main startup, we have a hash define where we can say where the non-secure code is starting. And then we have a new CMSIS function, which allows the secure code to access the non-secure main stack pointer. And then we're loading the first 4 bytes of the image directly into the main stack pointer of the non-secure code. So we're setting up the stack pointer for the non-secure code so we can start executing. We then take the start address +4, which is the reset handler, and we load the value that's stored in here directly into the into a function pointer, and then we call that function pointer. So that will now jump us to the reset handler that's in the non-secure code. So we've come into main, we've set up the non-secure stack, and then we've jumped directly to the non-secure code. And now our main application can start. And from there, once our code is running in here, it will be able to make calls directly to secure functions in the security partition. Now, in order to be able to do that, when we develop our secure functions, we can define them as as entry points to our code. So here we have an attribute, and this allows us to define this function as callable from the non-secure code. So this will now generate the veneer table, which is a secure gateway, followed by a branch instruction to the actual function. So the function will sit in secure partition. The veneer table is sitting in the non-secure callable area. And then we have a header file, which is given to the non-secure code that will, when it calls the secure functions, it will enter at this point and then branch and execute the main function. Similarly, if we want to call functions that are in the non-secure region and we're in the secure region, we can define a function pointer that allows us to call the non-secure functions. So again, typically we'll enter with a call from the non-secure region to a secure function. We'll pass a callback value that will be placed into the function pointer, and then we can call the function in the non-secure region. But this function pointer has another attribute that labels it as being able to call the non-secure code. So this will then generate the correct instructions and returns within the underlying assembler code. So in our non-secure library, we can set this up exactly the same way. So we create a non-secure project. We tell the software model that it's in this non-secure mode. Again, we have a choice of libraries. This should also be disabled because we're going to use a similar scatter file. And then this will add the normal startup and system code. The partition file is actually also included on the non-secure project, but it's not used and it's removed. And here we have the scatter file for non-secure, for the non-secure layout of the chip. And then we're also including this the veneer library, which provides effectively the entry points to the non-secure code. So then we can start building up our main code, and we can make calls to the secure functions. Now, we've got these two separate programs. We're going to be running most of our code in the non-secure project, but we are going to make calls to the secure code, which is effectively a separate programming. So if we want to have a full debug view of both projects, in the debugger, we can add a script file that will load up and program the flash of both regions, and will also load both symbol sets, so we can seamlessly debug between the two projects. So we can be running code in non-secure. When we jump to the secure region, we still get C-level debugging. So this is done by the load command, and then this additional keyword on the end, incremental, basically means add the symbol sets together. So this now gives us a complete debug view across both projects. If you've got high value IP, you can load that or pre-program that into the secure region, and then simply not provide a symbol set to the end user. So now they'll be able to debug only their own code in the non-secure region. You can also lock down the debugger so that when they call a secure function, it will execute the secure function and return to non-secure and not give them a debug view of it. So we have a number of options that we can deal with when using a debugger. Within the debugger, we also have support windows for the security attribution unit and the memory protection unit. So again, in the early stages of debugging, we can look at the chip and see exactly how things are configured. Generally, we're going to set up the SAU and leave it, so we can look at this in the early stages. The memory protection unit we'll set up and generally modify that on the fly. So having a very good view of the memory protection unit, it will be incredibly useful. Now, we also want to use an operating system with our Cortex-M 33. So there's been a lot of debate about where the operating system kernel should sit, and the chip is designed so that it could sit in the non-secure world or the secure world. And again, there's a lot of debate about which is best. However, sort of come to the conclusion that actually the kernel isn't holding any really privileged or secret information. So we can actually place it in the non-secure world. And there are a number of advantages to that. First, that means that we can minimize the code size of our secure code. So we're just keeping the security and the confidential data in there to a minimum. It also means that if we have the operating system here, you can use any RTOS that you want. It just has to call the functions that are in the secure area. So we're not forcing you to use a particular RTOS. When we're in the field, we will need to do software updates, but we don't really want to touch the secure world, or we want to upgrade that as minimally as possible. So by placing the RTOS in the secure region, we can happily update that. We can update middleware or any other code that we have. So placing the RTOS in the non-secure makes a lot of sense. One problem that we have, though, is that when we're making calls to secure functions, we may have multiple threads running. So if they make a call to a secure function, there's a task switch, and then there's another call to the secure function. There's no visibility in here for the context switching. So we have to provide some support within the secure code to manage the context switching of the RTOS. So we don't make multiple calls to a function from different threads and corrupt its variables. So there is some mitigation we have to do in here. So in the non-secure project, we would simply now add our operating system as normal, and then we can start developing code as we looked at in the second week. So the RTOS is essentially the same to use, but we just have to add this context management. So the first step of doing that is to make the RTOS kernel aware of which threads are going to call functions that are in the secure world. So in here, we have our thread attribute, and inside here, we have this TrustZone module support. And if we set that to true, then we're telling the kernel that this thread is going to make calls to the secure world. If we leave it at 0, then it's only going to access code that's in the non-secure world. Okay. So now when we start the thread, the kernel will assign an integer number to this thread, so 0, 1, 2, 3, so that when we call into the secure world, we can work out which thread is actually has made the call. And in order to do that, we need to add some context management functions to our secure project. So again, here we have a user code template in our secure code, and then we add this RTOS context management. So this is a small number of functions, and they're only a few lines each, but they essentially will take the process stack that's in the secure world, and it will divide it into a number of slots. So this will be the same number as the threads that are going to make calls into the secure world. And then each of those slots is given an arbitrary number of bytes, so that's up to you. And then we have an array of structures that are used to manage those slots. So each of the structures, so structure 1, structure 2, down to structure 7, has the stack top, the size, the stack limit, and then the current value of the stack pointer. So when we do a context switch, the kernel will say which thread is scheduled, and we'll know that from the TrustZone ID number, and then we can load the stack values into the active stack frame. So for example, if we start off with thread 0, we'll set the the current value of the stack. We'll set the size of the stack, and we can also then program the stack limit register so that if we overflow the stack, we'll spot that immediately. If we do a context switch to the next thread, then we swap to the next slot within the process stack. So this gives us a simple method of doing multi-threaded access to secure functions. Now, setting all of that up for a simple project, we can do that manually. But as we get more complex projects with multi-core systems, with multiple processors that have got TrustZone, so we've got different processor with their own resources. They've got both the secure and non-secure regions, and then inside those code we've also got operating system threads with their own stack spaces. Then our whole memory map starts to get quite complicated. So in order to be able to develop complex applications, and this is not really just for security, but as our applications are getting more complicated, we need to be able to manage these increasingly complicated resource management on the devices. So they have a new CMSIS standard, which is called CMSIS Zone. So this is essentially a standard and utility for partitioning the system. Okay, so it allows us a very straightforward way to manage where code into what region code is allocated, and generate both the linker files and also the runtime code as well. So this is, again, like all of the CMSIS standards, it's an open source standard, and it's designed to work with all of the major tool chains. So again, it's not specific to the ARM tools. Within the CMSIS documentation, we have a description of how it works, and underneath it's based on a templating technology called FreeMarker. So this basically allows us to create default template files of, for example, our script files, our partition header file. And inside there, we have tags, which are placeholders. So as we then define our CMSIS zone, those placeholders can be updated with our project values. And then we can generate the text files for our actual project. So part of CMSIS Zone is CMSIS Zone utility. So this is an open source free tool that we can download. It sits currently within the Eclipse IDE. So again, you can download it as a full version of Eclipse, or it's also available as a plugin if you're already using Eclipse as a development tool. And again, you can find it on GitHub. It's a bit of a hack round to find it, but version 1.0.0 is now available for use. You lucky things. So here, the first thing that we actually need to do is install our device packs for the devices that we're going to use. So again, within Eclipse, like within MDK, there's a pack installer available. So this allows us to connect to the cloud server and download and install our different packs for whatever microcontroller we're using. And then within the packs, we have information about the resources on those devices that will automatically be used by CMSIS Zone. So you don't have to spend a large amount of time defining your raw memory map before we can actually generate some useful files. If you already have the pack installed in your system for another tool, it's possible to point at that repository. So here in the Windows Preferences CMSIS packs, you can then set up a path to an existing repository. So we don't have to duplicate things that are sitting on our PC. So now within CMSIS Zone, when we create a project, we can go in and create a new project. Here we have a CMSIS folder. Here we can then create the CMSIS Zone project. And When we select that project, we've got two choices. We can load an existing resource file. So this is the basic description of the processor, or we can select a device, and then TrustZone will create the resource file from the pack description. So if we generally will select this option, and then it will show us the pack repository, and we can select devices from any of the packs that we've got installed. So this will now load the memory description and also the system viewer description file, the SVD file, that's used to generate debug views of the peripherals. So those contain all of the register descriptions of the peripherals, which can then be imported into TrustZone. So now we have a series of tables to work through. So when we begin, we have an initial resource map. So here's one that's been sort of partly completed earlier. So it will describe the flash memory, SRAM, and peripherals. We can then create sub-regions in here. So if we want to split one block of flash and give it non-secure and secure regions, we can add a memory region that subdivides it. And then we can specify how that region is going to be used, whether it's secure, non-secure, whether we're going to run privileged or unprivileged code. If this is a startup region and we want to locate the vector table there. Again, if we've got other bus masters are going to access this as well. So we can build up a basic description of the layout of our device. Next, we can create new CMSIS zones. So here we have our secure world and our non-secure world, and we can start to add memory regions between the secure and non-secure region. We can also go down to the operating system. We can define threads. We can then allocate those memory regions as well. So this is currently in development. So the so here, when we create a description of the operating system threads, we will be able to enable the MPU support, and that will then generate runtime tables, so that when we do task switch, we'll program the memory protection unit to effectively sandbox that thread. Now, this isn't in the current release, but I believe it should be out by the end of the year. So once we've set up the description of our project, we can simply press the generate code, and this will then automatically generate the scatter files for our secure and non-secure projects, so the linker files. It will create the partition file, so we'll be able to set up the security attribution unit, and then it will also create a basic memory layout file, which we can use within both the secure and non-secure code. Additionally, for a given processor or microcontroller, it will create a system isolation config. So this will be used to program the global bus filters, so the memory and peripheral protection filters that are on the bus interconnect. So this then creates, between the security attribution unit within the Cortex-M33 and the global bus filters, this will then create a secure execution environment. So we've now got two projects. We've got the startup code that will partition the chip. Ultimately, we'll then also have the memory protection code that will run with the operating system in real time. We can make calls across into the secure code, and we can also do context management for the operating system as well. Now, if we've got our secure services in here, so things like cryptography library, secure storage, attribution, attestation, etc., then we've got quite a large number of functions in here. So we have a very nice, strong isolation between them. And if we're going to just make direct function calls across to our secure functions, what we'd actually end up doing is creating lots of entry points into our secure firmware. So this is akin to having a very big castle wall and then creating dozens and dozens of gates in it. So lots and lots of holes in our nice solid wall. So we don't really want to make direct calls from our user code into the secure code. So what we're going to have a look at tomorrow is the overarching security model and the trusted firmware for the Cortex-M33. So this implements a secure partition manager. So we have a limited entry point to the secure partition. And then all of our crypto services are running in their own partition environment. And we can then further lock these down with memory protection regions so that we can create higher levels of security. So we'll have a look at this tomorrow, how it's set up, how we consider all of the main top 10 security concerns and address those with the ARM platform security model and also the trusted firmware. So although this looks complicated, it's actually provided as a reference software so that we don't need to go and architect and design this ourselves. We can go in and start using it. So we'll start to have a look at that tomorrow. There is a website for this, www.trustedfirmware.org. So again, if you want to have a look at that, but again, tomorrow we'll restart at about 1:30, and we'll have a look through the overarching security model, trusted firmware.